So here's the problem we finished up with in class on Wednesday. I'm looking at which substances act as a base. So remember, we identify our acid and base based on the context of a particular chemical reaction. And so remember that we're looking for acids to be proton donors and bases to be proton acceptors. So what I want to do is look at each substance and see how it behaves as it goes from reactants to products, and then we'll look at it in the reverse direction because we are a reaction at equilibrium. So we have our equilibrium over there, which means the reaction's going in both directions. So I look at HF, which goes to F minus, and I see that as it goes from HF to F minus, they differ by a single proton. It's donating a proton in that process. And so as a result, the HF is an acid. Now, remember that we do have to have acid-base pair on either side if we have this. So we think the water is probably going to be the base, but we still want to look at it to see what's happening as we go from reactants to products. So I go from H2O to H3O plus. Again, they differ by a single proton. That's how I identify the pair that I want to look at. And I see that H2O is acting as a proton acceptor, so it's going to be a base. Now what I want to do is look at the opposite side of the equation and say, well, what's happening as I go in the reverse direction? Because that's what that equilibrium arrow means. So as I go from H3O plus to H2O, I see that it's donating a proton, so this is behaving as an acid. And as I go from F minus to HF, it's accepting a proton, so that's acting as a base. So what we notice here is we have an acid and base on both sides of the equation, and we also see that the substance that was an acid, after it donates its proton, becomes a base, and vice versa for the base to acid. So our correct answer is C, H2O, and F minus. So now we want to look at the difference between strong and weak acids and also how we identify what acids are. So first of all, when we have a strong acid, so something like HCl is a strong acid, it completely dissociates in water. Here we're showing the shortened version of the H+, we're not showing the H3O plus ion and water, we're just showing H+, but we see that it dissociates into H+ and Cl-. Now these are happening in water even though it's not explicitly shown. But a strong acid will dissociate completely, and it's a strong electrolyte because that's what makes a strong electrolyte a strong electrolyte. It dissociates completely into its ions. Weak acids are weak electrolyte. The strong and weak of an acid has nothing to do with the damage it can do or how dangerous or toxic or anything it is. It's simply about how it behaves in aqueous solution. So a weak acid, and HF is an example of that, does not completely dissociate. And so HF is a weak acid, but it also can be a very dangerous acid because these HF molecules are so small that they can actually start absorbing into your skin and doing things like displacing calcium from your bone and messing up your blood chemistry, and lots of pretty nasty things can happen. And so what we see is that this is a weak acid, and we know it's a weak acid based on the equation here because we have our equilibrium arrow. We still show it dissociating into the H+ and F- ions, again the abbreviated form, but we have that equilibrium arrow, which means the reaction is actually proceeding in both directions, and we have some HF molecules present as well as some of the H+ and F- ions present. Now to identify an acid, we generally look for a compound that starts with a hydrogen. About the only one we see that starts with a hydrogen that's not an acid is water, and even in some contexts, water will behave as an acid. So here we have HCl, HF. We also see some other examples down here: HCl, HBr, HI, HClO4, HNO3, H2SO4, and these are what are known as the 6 strong acids. And so the way we distinguish between strong and weak acids is we memorize this list. We memorize this list of 6 strong acids and know that any other acid is going to be weak. Now the other type of acid that we've looked at is our organic acid. So we looked at our acetic acid, which looks like this, has that carboxylic acid functional group, and all of those organic acids are all weak acids. So they all have this COOH group, and those are going to be weak acids as well. When we look at the reaction between acids and bases, we often call it a neutralization reaction. And what we're saying is we're neutralizing it. When we end, we have neither an acid nor a base, but we have a neutral solution. And so when we react, then we get acid plus base yields salt plus water. And I'm not going to expect you to write out these equations. You don't have to predict the products or anything like that, but I do want to show you how we find it just because it can be useful when you're looking at equations to try to figure out what's going on in the process. So notice here we have HCl, so we get the anion from our HCl with the cation from our NaOH, which is our base, and those two substances actually come together and form NaCl. And what we're left with on the other side is H and OH, and they form a water molecule. And so we see this happening, but the big thing we're worried about here is acid and base, salt and water. And we're going to be seeing this again when we start to look at buffers, which are substances that help control the pH of a solution, and we have lots of buffers in our blood to do just that. So when we're dealing with solutions, whether they're acidic or basic, we can also see this in other solutions, but we use this a lot when we're looking at acids and bases, is we have to use molarity. And so what we want to look at is to determine the molarity of a solution prepared from 20 grams of LiCl in 150 milliliters of solution. And we're given the molar mass of LiCl. So the first thing I want to do is remember what the definition of molarity is. So molarity is moles of our solute, and in this case it's going to be our lithium chloride over liters of solution. So what I need to do is I need to figure out both the moles of my solute and the volume in liters of my solution. So when I look at the problem, I notice that I'm not given the moles of lithium chloride, but I am given the grams of lithium chloride, and I'm also given the molar mass, although you could find that if it wasn't given. So I can use the mass and the molar mass to actually find the moles of lithium chloride. And so now when I look at this, my units of grams have canceled out, and I'm going to take 20 divided by 42.39, and I get 0.472 moles of lithium chloride. So now I know my moles of lithium chloride that I need for the numerator. I've got my volume of lithium chloride, it's in milliliters, so I can convert that to liters by dividing by 1,000, and then I can find my molarity by saying M for molarity equals 0.472 moles of lithium chloride over our total volume of solution, which is 0.150 liters of solution. So I really just had to find moles and had to find liters. So it's not always given to you in the units you need, so you might have to do a little bit of conversion. And what we get here is 3.15 molar lithium chloride solution. So another unit looking at concentration units, we have here a 13.50 gram hydrocarbon sample. We're really not worried about the identity of the compound. We know we have 13.50 grams of it, and it contains 85.63% carbon by mass. So if we have a hydrocarbon, we know that the only elements in it are carbon and hydrogen, and we know that it's 85.63% carbon by mass. So remember, when we look at mass percent, that's equal to the part, so the mass of whatever substance we're talking about, so mass of the part, in this case we're looking at carbon, over the whole mass, times 100. So that relationship is always going to be true. We can also write this expression, we can write a relationship rather with that percentage. We can say, well, if I have a sample that's 85.63% carbon, I can also say that for every 100 gram sample, I have 85.63 grams of carbon. So just like on an exam, if you got 85% of the points, if there were 100 points, you would have gotten 85 points out of that. So that's just the relationship that we get from that percentage. So now to actually solve the problem, what we need to do is say, well, we actually only have 13.5 grams of our sample, and we know the percentage based on 100, so we're going to say 13.5 grams of the sample. Notice that this does say the hydrocarbon sample, and so therefore on the bottom I'm going to put 100 grams of my sample, and on top goes the 85.63 grams of carbon. Notice here that we have grams of the sample canceling with grams of the sample. We can't cancel grams of the sample with grams of carbon, so you've got to be careful which one goes on the top and which one goes on the bottom. Now we can find our percentage or our mass of carbon in this sample by simply taking our 13.5 times 85.63 and dividing by 100. And we get the value of 11 point, we need 456 grams of carbon. And that looks like a reasonable value. We see it's most of the sample, but our sample was 85% carbon, so we're going to expect a value pretty close to that 13.5 grams. So here's a question, which one is equal to 15 ppm? So pause here, think about that for just a second. So we see our answer is actually A. Anytime we see ppm, we can rewrite that as milligrams per liter. Remember this, micrograms per liter, will be equivalent to ppb. So the last thing we're going to look at here with concentrations, and this deals with dilution. And so we see this quite a bit because whether we're in the lab, in a research building, or in healthcare, sometimes we have to worry about things being diluted, that it comes at a higher concentration and we actually have to dilute it down to the amount we want. And so what we do is we look at this problem and we see that we've got a 2.5 molar solution with a volume of 25 milliliters. So I look at the way this is written and determine that the 2.5 molar and 25 milliliters go together. They're describing the same sample. And then we see it's diluted to a final volume of 65 milliliters, and we're looking for the concentration of that final solution. So I know that I go to 65 milliliters, but I don't know what the concentration is, but I know I want it in molarity. And so what I actually have to do is set up what we call the dilution formula. So we have C1V1 equals C2V2. So C's are concentration and the V's are volumes. And so notice that there's no chemical reaction going on here. We're simply adding more solvent, so we're increasing the volume of the solution. As a result, we see a change in the concentration. So what I'm going to do is I'm going to plug in my values. I know for my sample here I've written in red, I've got 2.5 molar and I've got 25 milliliters. Now, a couple things to note. One, I need to make sure I pair the numbers correctly, that these are both describing that same particular sample, which was the initial solution in concentration and volume. And then I've got to say, well, what am I going to? And in this case, I don't know what C2 is, but I do know my volume. Now I can actually solve for my unknown. Now I don't have to have this in units of liters, but I do have to have those volumes in the same units. So it doesn't matter whether they're milliliters or liters as long as they're the same. We can also use this formula with other units of concentration, but again they all have to be in the same unit. And so because I'm diluting this solution, I do expect a lower concentration, and that's what I get when I solve the problem. I get 0.962 molar. So that's my concentration of the solution.